Answer the following questions. And question is, time period of a particle in SHM depends on the force constant K and the mass m of the particle, so that time period t is equal to 2 pi under root m by k. A simple pendulum executes SHM approximately. Why then is the time period of a pendulum independent of the mass of the pendulum? So we are given that if some object performs a simple harmonic motion, then its time period is given by this formula, okay, where t is equal to time period and m is the mass of the object and k is the spring constant. And it is asked that when some pendulum performs SHM approximately, then why its time period is independent of the mass of the pendulum. So if I solve part A, if I consider a pendulum, suppose this is the mass of the pendulum m, this is the bob of the pendulum with mass m, and length of the string bl, and it is given some small angular displacement. This is given small angular displacement. This way is angle theta. And if I consider the forces acting on this bob of the pendulum, this is the mg. If this angle is theta, then also this angle will also be the theta. And if I break mg into two components, this will be mg cos theta, and this one I am writing it as here mg sin theta. Okay, so this mg sin theta will provide the necessary restoring force on the pendulum. So I can write as F restoring is equal to minus mg sine of theta. Okay, where negative sign represents that restoring force is opposite to the direction of displacement. Further, I can write as Fr is equal to minus mg sine of theta. If I consider this triangle suppose A, B and C. This length is, if I say x, and this length of the pendulum is L. So in triangle ABC, sine theta is equal to x over L. This implies restoring force is equal to minus mg by L into x. This implies I can also write as force restoring is equal to minus some k prime times x, where k prime is equal to mg by L. If I put this value of k prime for the case of pendulum in the formula of time period, we know given that time period is equal to 2 pi under root, what we are given is 2 pi under root m by k. But in the case of pendulum, we have given the name k prime. So on substituting the values of k prime, I will get as mg over L. This m gets cancelled. So I get formula for the time period as 2 pi root L over G. which is completely independent on the mass of the bob of the pendulum. Now, coming to the question D, we are asked the motion of a simple pendulum is approximately simple harmonic for small angles of oscillation. For large angles of oscillation, a more involved analysis shows that the time period is greater than 2 pi under root L by G. 2 pi under root L by G. We have already calculated this time period in part A, and we are asked that when the angle of oscillation is not small, then the time period of oscillation is more than this value. So the formula that we have derived, since we derived that, if we consider part B, so continuing with the part B, since we have derived with that force restoring is equal to minus mg sine of theta, and we know if theta is small, we can write this restoring force is equal to mg of sine of theta. But for large theta values, sine of theta, sorry, this will be theta. As for the small theta values, we can write restoring force as minus mg theta, because for small theta, sine theta is approximately equal to theta. But for the large theta values, sine theta is smaller than theta. This implies, which means omega is less than under root g by L, and we know time period is 2 pi by omega. And if omega decreases, then time period increases. This formula for the omega is equal to root g by L, is only valid when sine theta is approximately equal to theta. However, when theta is large, however, when theta is large, sine theta is less than theta. This implies omega is less than this value, and we know time period is 2 pi by omega. If omega decreases, then time period increases. So we have solved for part B as well. Now part C says a man with a wristwatch on his hands falls from the top of a tower. Does the watch give correct time during the free fall? We are given the situation in the part C that a man falls from the top of a tower having wristwatch in his hands, and when he will fall from this tower, we are asked that the wristwatch will give correct time or not. We just need to know the watch will give correct time only when its time period doesn't change in free fall. Okay, And we know in case of wristwatch, the time period is given by 2 pi under root k by n. It is totally independent of the gravity, as the working of wristwatch is based on the spring system. Spring system, whose time period is given by this formula, where k is the force constant and m is the mass. So there will no any effect on the time period. Hence, we will get the correct time. The watch will show us the correct time. Now, in the part D, we are asked what is the frequency of oscillation of a simple pendulum mounted in a cabin that is freely falling under gravity. So in the option D, we are given that there is one cabin. I read over this in a better way. There is one cabin and one pendulum is being suspended in that cabin, and this cabin as a whole system is going under free fall. We need to determine its time period and frequency. So time period of oscillation of pendulum is 2 pi under root L by G effective. Effective value of the acceleration due to gravity. So if I take 1 by time period, that is frequency is equal to 1 by 2 pi under root G effective by L. So if I consider this cabin as one non-inertial frame and one observer sitting in the cabin observes the pendulum, so we can see there is one G acting downward on the bob of pendulum, and we will associate another value of G in upward direction as pseudo force, because my observer is sitting in the non-inertial frame, and from this I can consider G effective on the bob is 0. This implies value of frequency will be 0.